Hi, I'm Ethan, and I'm going to talk about our paper Streaming Weak Submodularity, Interpreting Neural Networks on the Fly. This is joint work with Alex, Moran, and Amin. In many machine learning applications, it's important to explain the predictions of a black box classifier. For example, let's consider image classification. If I retrain the Inception V3 neural network to label images as one of 5 types of flowers, then can I trust why the network classifies this image as sunflower instead of daisy? The final sigmoid activation corresponding to sunflower is 4 times 10 to the minus 5, but why? First, let's see how to turn interpretability into a subset selection problem. The idea is to partition the image into interpretable chunks using a segmentation algorithm. Then we can turn on only certain segments of the image, replacing the rest with a neutral background, and check the sunflower activation for these new images. For this random subset of regions, it's quite low, but the activation for these 2 regions is about 1/2. And for these 5 regions, it's about 0.8. We see the same thing for the label daisy. More generally, we can define a set function to be the activation for a subset of the image minus some reference activation. If the set is size k, then our explanation uses only k segments. So the new goal is to find the parts of an image which contribute the most to a given label. And now we can go from image to segmented image to sparse explanation. This leads to the following optimization problem. Given a set of n items and a set function f, select a set S of size k which maximizes f of s. This problem has many applications, but in the paper we focus on neural network interpretability and sparse regression. There are 2 potential issues with this approach. If we make no additional assumptions, then the general problem is NP-hard and hard to approximate, meaning we need to check all n choose k subsets to find the best one. Moreover, in our application, each call to f requires performing inference on a deep neural network, which could take seconds, and so we also want to reduce the number of function evaluations. To address this second issue, we would like to design streaming algorithms, which make one pass over the data, maintain sublinear number of elements in memory, and minimize the number of function evaluations. Previous work has proved that efficient greedy algorithms obtain good approximation ratios when the set function is assumed to be submodular or weakly submodular. A streaming greedy algorithm also exists for submodular functions. In this paper, we combine the 2 assumptions and design and analyze streaming algorithms for maximizing a weakly submodular set function subject to a cardinality constraint. I'll briefly explain the key idea behind the algorithm. Many greedy algorithms use a quantity called the discrete derivative, which checks how much the function value can increase by adding to what we've already selected. Our algorithm computes an incoming element's discrete derivative and adds the item if it exceeds a predefined threshold. We improve this algorithm, removing the dependence on tau, by running many instances with exponentially spaced thresholds. Here's one of our experimental results, which compares the running time of our algorithm to a related approach which solves a different, more expensive optimization problem. In summary, we present a combinatorial framework for interpreting black box neural network predictions. We prove approximation guarantees for streaming algorithms under the theoretical assumption of weak submodularity, and show experimental results for interpretable image classification and sparse regression. For more information, please attend our talk on Tuesday, December 5th, or the poster session that evening.